Welcome dear students, we are on the CEC Gurukul lectures. Today's topic is the capacitor. We are in the series of basics of electronics, and in this series we are discussing the various components of electronic devices. So in today's discussion we will take the capacitors. On the screen we are having the various type of capacitors. You see of the various sizes and of the various values. Now, what is the capacitor? In this lecture series, we will discuss that what is a capacitor and how it works, what type of capacitors we have, what is the dielectrics in between the capacitors. So, we start with the definition of the capacitor. What is the capacitor? Capacitor basically is a component which has the ability to store the energy in the form of an electric charge, producing a potential difference, that is the static voltage, as we all know, across its place, much like a rechargeable battery. Here we are having a capacitor which has a capacity to store the energy, which in the form of the electric charges, and it is work like a rechargeable battery. On the screen you are seeing that there is a component that is a capacitor. Sometimes we are having the various type of capacitor. You see on the screen that these are the various type of capacitor. Some in the round form, some in the tablet form, like that. These are the basic capacitors. So what is a capacitor? Which has a capacity to store the energy in the form of an electric charges, and electric charges which is produced because of the potential difference, that is the static voltage, and it works as a rechargeable battery. So capacitor is like a store the energy in it. Now a capacitor consists of two or more parallel conductive metal plates which are not connected or touching each other. It means in a capacitor we are having a two parallel conductive plates, and they must be at some distance, but are electrically separated either by air or by some form of good insulating material, that must be the dielectric material, like wax paper, like mica, like ceramic, like plastic, or some form of the liquid gel used in the electrolytic capacitors. Capacitor is the two parallel plates which are not connecting to each other, which are at some distance, and in between these two plates we are having some material which is the insulating, and that is the dielectric material. Example are waxed paper, mica, ceramic plates, and so on. The insulating layer between a capacitor plates is commonly called the dielectric. That is a dielectric material which is in between the two plates of the capacitor. Due to this insulating layer, DC current cannot flow through the capacitor as it blocks it, allowing instead a voltage to be present across the plates in the form of an electric charges. It means DC current can't flow through the capacitor. When used in the direct current or the DC circuit, a capacitor charges up to its supply voltage but blocks the flow of current through it because the dielectric of the capacitor is non-conducting, and it is insulating, and basically as it is an insulator. So it blocks the flow of current through the dielectrics when we use the direct current or in the DC circuit. However, when a capacitor is connected to a alternating current, that is the AC circuit, the flow of current appears to pass straight through the capacitor with a little or no resistance. It means AC current can flow directly through this capacitor. There are two types of the electrical charge, a positive charge in the form of photons and negative charge in the form of electrons. So we have two electrical charges. One side we have the positive charges and other side we have the negative charges. One because of the protons and another because of the electron. Now when the DC voltage is placed across the capacitor, the positive charge quickly accumulate on the one plate, while the corresponding and the opposite negative charge accumulate on the another plate. It means number of the positive must be equivalent to the number of the negative, and these separated through the one positive charge on the one plate and another negative charge on the another plate. For every particle of the positive charge that arrive at the one plate, a charge of the same sign will depart from the negative plate. Means the number of positive must be on the other side, number of the negative. Now then the plates remains charged neutral, and a potential difference due to this charge is established between the two plates. Because of this, the potential difference developed between these two plates. When the capacitor reaches its steady state condition, an electrical current is unable to flow through the capacitor itself and around the circuit due to the insulating property of the electric used to separate the plates. Means dielectric in between the two plates will separate these two plates, and it works to flow of the current inside the capacitor. The flow of electrons into the plates is known as the capacitor. Capacitor's charging current. The flow of electron into the plates is known as the capacitor charging current, which continue to flow until the voltage across both the plates is equal to the applied voltage Vc. Means when we apply the voltage across the two plates, then the electron must flow between the plates. And at this point, the capacitor is said to be fully charged with the electrons. Now, when the potential difference generated between the two plates because of the flow of the electron, then we can say a capacitor is fully charged because of the flow of the electrons. Now, the strength or the rate of this charging current. Now we can calculate the strength of this, how much energy we can store, and the strength or rate of charging of the current is at its maximum value when the plate is fully discharged. Initial condition, this is the initial condition, and thus slowly reduced in the value to 0 as the plates charge up to the potential difference across the capacitor plates equal to the source voltage. It must be the source voltage must be equal to the potential difference across the capacitor. Then we can say the plates are charged. The amount of potential difference present across the capacitor depends upon how much charge was deposited on the plates by the working of the two plates and the dielectrics. The potential difference present across the capacitor depends upon the charge, how much charge was deposited on the plates by the work being done by the source voltage. It depends upon the source voltage, and also by how much capacitance the capacitor has, and this is illustrated further. How much capacity of that capacitor, that depends, and how much and what type of the plates we are using, and what are dielectrics in between these two plates, that define the amount of potential difference present across the capacitor. Now this is the schematic diagram of the capacitor. You see on the screen that we are having a two conductive parallel plates and having the charge Q positive and Q negative. Q positive because of the proton and Q negative because of the electron, and the electric charge is produced in between that. You are seeing that in between these two plates we are having a dielectrics, and the charges plus and minus are connected with the voltage. Plus connected with the voltage Vc, source voltage connected with the positive, and negative connected with the negative, and these charges are separated. The symbol of this is in here, the two parallel lines and connected with the wire. The parallel plate capacitor is the simplest form of the capacitor, and it can be constructed using the two metal or metallized foil plates at the distance. You are seeing on the screen that there is a distance between these two conductive parallel plates and dielectrics in between that. So these two plates are separated by some distance, and these are parallel to each other with its capacitance value in the farads. It means the unit of the capacitance is farads, being fixed by the surface area of the conductive plates and the distance of the separation between them. It means the surface area of the conductive plate and the distance between these conductive plates, and the dielectrics plays an important role in calculating the capacity to store the energy in the capacitor. Alternating any two of these values alters the value of the capacitance, and this form the basis of operation of the variable capacitor. It means when we change the distance between these two plates and the surface area of the capacitor can change the value of the capacitance. The capacitors may be worked as a variable capacitors. So, altering any two of these values alters the value of the capacitance, and this forms of the basis of the operation of the variable capacitors. When we change the value of the capacitor will change. That's why it is called a variable capacitor. Also, because capacitors store the energy of the electrons in the form of the electric charge on the plates, the larger the plate and the smaller their separation, the greater will be the charge that the capacitor holds for any given voltage across its plate. Like when we take the larger distance between the plates, or when we take the electric charge on the plates, larger the plates, another smaller their separation, means we are taking the larger surface area of the plate and the separation between these two plates are less, then we are having a greater charge capacity there. So, greater will be the charge that the capacitor holds for any given voltage across its plates. In other words, larger plates, smaller distance, more capacitance we can have. If we increase the capacitance of a value, then we have a larger plates, smaller distance between them, the capacitor value will increase. By applying the voltage to the capacitor and measuring the charge on the plates, the ratio of the charge Q, charge represented by the Q, to the voltage, the ratio of charge by voltage will give the capacitance value of the capacitor, and we denote is that it as a C is equal to capacitance of a capacitor, C is equal to Q by V. This equation can be also be rearranged, then we can find out the charge on the plate, that is Q is equal to C into V. If we calculate the charge on a plate, then we should know the capacitance into the voltage applied. Here, if we take the capacitance, then how much charge is there and the voltage applied across the capacitor. So, that can be calculated. Capacitance C is equal to Q by V, and if we calculate the charge on the plates, then we can use the formula Q is equal to C into V. The charge is stored on the plates of the capacitor. It is more exact to say that the energy within the charge. What I am saying, that what we are saying, that it's the capacity to store the charges. So we can say energy within the charge is stored is an electrostatic field between the two plates. The energy which is in the form of the electrostatic field. When the dielectric current flows into the capacitor, it charges up, so the electrostatic field becomes much stronger as it stores more energy between the plates by the electric flow currents. Likewise, as the current flowing out of the capacitor discharging it, the potential difference between the two plates decreases and the electrostatic field decreases as the energy moves out of the plate. So, these are the working. The property of the capacitor is to store the charge on its plates in the form of an electrostatic field, and that will known as the capacitance of the capacitor, which stored the charge which is in the form of the electrostatic field, and that is the capacitance of a capacitor. Now the question, how we calculate the capacitance of a capacitor? By knowing the value of the surface area of the plates and the distance between that, we can find out the capacitance of a capacitor, means the storage capacity, or we can find out the electrostatic field inside the capacitor. Not only that, but the capacitance is also the property of the capacitor which resists the charge of the voltage across it. It will not change the voltage across it. It resists the change in the voltage that is applied. Not only that, but the capacitor is also the property of the capacitor which resists the change of the voltage across it. Now the question, what is the capacitance of a capacitor? How we will calculate the capacitance of a capacitor? How much is the ability to store the electric field, or we can say electrostatic field inside the capacitor? So capacitance is the electrical property of the capacitor and is the measure of the capacitor's ability to store an electrical charge into the two plates, with the unit of the capacitance being the farad, and it is abbreviated by capital F, named after the British physicist Michael Faraday, who performed this experiment, who discovered the capacitor. The capacitance of a capacitor is defined as being that a capacitor has a capacitance of 1 farad when a charge of 1 coulomb is stored on the plates by the voltage of 1 volt. Then we can say it is a 1 farad. 1 coulomb stored because of the charge, because of the voltage applied, which is the 1 volt. So 1 farad we can get, and that is the capacitance of a capacitor. Capacitance is represented by the C, but the unit is the farad, and that is represented by the F. The capacitance C is always positive in the value and has no negative units. Always we define that there must be a storage of the charge electrostatic field inside the two plates. However, the farad is a very large unit of the measurement to use on its own. So sub multiples of the farads are generally used, such as the microfarad, when we define it 10 to the power 6, nano 10 to the power minus 6 farad, 10 to the minus 9, that is the nanofarads, picofarad, and so on. You see on the screen that here we are having the standard units of the capacitance. If we talk about the microfarad, then it is represented by the mu f. 1 mu f is equal to 10 to the power minus 6 farad. And nanofarad, that is represented by the nf, and its value is 10 to the power minus 9 farad. Picofarad, that is represented by pf, and its value is 10 to the power minus 12 farad. So these are the standard units of the capacitance. That is the 10 to the power minus microfarad, nanofarad, and the picofarad. How the capacitors are connected in the circuit? That is another question. The capacitors connected in the circuit, in an electronic circuit, in the series or in the parallel form. So we can say the capacitor series and the parallel capacitors are there. We connect the capacitors in the series, or we connect the capacitor in the parallel. Now, what are the difference between that? That when we connect it in the series and we connect in the parallel. So when the capacitors are connected in the series, the total capacitance is less than any one of the series capacitors, individual capacitors. The value of the total of the capacitance when it connected in the series is less than that of the one of the capacitor which is attached here. Why it is so? Then it is, if the two or more capacitors are connected in series, the overall effect is that of the single, which is equivalent capacitors having the sum total of the plates spacing the individual capacitor. As we have just seen an increase in the plate spacing with all other factors unchanged, result is the decreased capacitor. As we increase the plate spacing, it means the spacing plays an important role. If the spacing is less, then the capacitor is more chargeable. The capacitance will be more in the capacitor. You see on the screen here we are having the series capacitance. Here you see the two capacitors C1 and C2 are arranged in a series, and here the equivalent capacitor is defined as the C total. Now the series capacitor, the C total is equal to 1 by C1 plus 1 by C2 plus 1 by Cn. This is the formula when it is connected in the series. Now when the capacitor is connected in the parallel, next is the parallel, first is the series. When connected in the parallel, total capacitance is the sum of the individual capacitances. If the two or more capacitors are connected in the parallel, the overall effect is that of the single equivalent capacitor having the sum total of the plates area of the individual capacitor, as we have just seen the increase in the plate area and all factors unchanged, result in the increase in the capacitor. You see on the screen here the two capacitors are connected in a parallel, And the parallel capacitors formula, C total is equal to C1 plus C2 plus C3 and Cn. So there we say that in this series that the capacitance will decrease, but here in this the capacitance will increase as of the individual capacitors. Thank you very much.